Hi, thanks for joining me on this video. I want to start off by just posing one question to you. Isn't it time that we transcended the dark art of prompt engineering? Now, I'll elaborate on exactly what I mean by the dark art of prompt engineering. The era of large language models has brought with it this discipline that we call prompt engineering. And there are even cases of people being employed and being paid really high salaries to be prompt engineers. It seems like if you have the capacity and skill to be able to concoct recipes to tease out outputs from large language models, that's something that a lot of people right now on the marketplace are looking for. However, if you have experimented yourself with prompt engineering or you have done a little bit of research, it seems to be very much a fuzzy discipline. It feels almost more akin to alchemy than it does to computer programming. To illustrate this, we can look at one of the popular prompting frameworks called React. So I've put on screen now the actual prompt behind the React prompting framework. This is taken from the DSPy paper itself just to illustrate to you exactly what goes into these prompts, because often when you use them through frameworks like LangChain or Llama Index, the prompt is itself is hidden from you. If you look at the text on screen, you can see not only is it verbose, but there is actually quite a lot of hard coding in there, and it's really meticulously crafted. In actual fact, what we have here is around 45 lines of text with careful instructions to guide large language models to act in the way that we want them to act following this React framework. So, what's the issue with hard coded text prompts like the React prompt that I've just shown on screen? The first issue is about maintainability. You can see 45 lines of text prompt there, and fortunately, it's quite easy to follow. But you can imagine a situation in production where maybe you have a pipeline of large language models operating together, and each might be using a different prompt framework. All of a sudden, as an engineer, you have to start dealing with these long bits of hard coded text and start understanding how they interact with each other. That becomes quite difficult to maintain over time. And as you can imagine, engineers do swap in and out of projects. So 5 or 6 engineers down the line, the prompt starts to look very confusing. The other issue with the hard coded prompts is that they are brittle. They're brittle in the sense that they do not adapt to your specific use case or the data that you might be operating with, and they do not adapt to the large language model that you might be operating with. The React prompt on screen was very much fine tuned or created to perform particular tasks. If you take time to reinspect that prompt, you'll see that the examples provided or the types of instructions provided were answering specific types of questions. But then, how does this prompt translate to something outside of the domain that it was written for? The answer is probably not that well, or at least there might be some kind of deterioration in performance because it's hard coded. It can't adapt to a different domain outside of itself. So that's the issue with those are the issues with hard coded prompts. The first, obviously, being they are difficult to maintain, especially when you start growing your applications and you start using systems of large language models. The second aspect is that they are brittle. They do not adapt to the large language model that you're using, or indeed the data that you are using, or the domain that you're operating with. So hopefully you're on board with my initial premise or my opener starting off this video that prompt engineering is a bit of a dark art right now, and it's time that we transcended prompt engineering as it's traditionally done by hand typing and hard coding long text prompts. But is there actually an alternative? The answer to that is yes, there is an alternative. now that we can use in the form of an open source framework called DSPy. To understand DSPy, it's important to grasp a few of its fundamental concepts. I'll spend this next portion of the video talking about some of those fundamental concepts and hopefully explaining them to you in a way that you can understand and move on to trying out DSPy for yourself. Before I get into the explanations, there are a few things that accompany this video that should help you to grasp the framework. There's a technical article that I have written, and as soon as that's published, it will be linked in the description to the video. There is also a Google Colab notebook with the analysis that I've performed. I'll be introducing a bit of that analysis in the video, but the analysis is covered extensively in the technical article. Please take some time to have a look at both to help you really get to grips with the framework. To understand DSPy, there are three components that you really need to grasp. These are modules, signatures, and teleprompters. I'll go through each one by one in hope of explaining them to you in a way that should make sense. But I'd like you to also pay attention to the GIF that will appear on screen that illustrates the process. So hopefully by me talking it through and you seeing the GIF and seeing how these things work in motion, you should get at a high level how DSPy works. So the first component I introduced are modules. So DSPy provides composable and declarative modules for instructing large language models. They can be used to create arbitrarily complex pipelines, which we will refer to as programs. So that's a key thing to understand. You can use modules, stack them together essentially like Lego blocks to create arbitrarily complex pipelines, and we call these programs. This is really key to understand this. The next component is the signatures. So signatures define the input and output behavior of each module. Here is where there is some hard coding. It is minimal, but you can't really escape it when it comes to large language models because they are semantic. They do interpret text at the end of the day. So because signatures define the input and output behavior of each module, the signatures need to be precise and short because they need to be interpreted by the large language model. So obviously, the more powerful your model, the better it is at interpreting those signatures. But because we want our programs to be as model agnostic as possible, make them precise and short as you possibly can. The last piece of the puzzle to understand are the teleprompters. So DSPy provides teleprompters for compiling programs. So compiling in this sense means to optimize your program against a defined performance metric for a given large language model and a given training data set. So obviously here your training data set represents the domain that you're operating in. So if you're training a large language model, if you're building a large language model based application to answer math problems, let's say, your training data set will probably be a sample of those types of math problems that you want it to answer. So those are the three components that you need to be cognizant of. So there are modules, signatures, and teleprompters. Great. So now that we've introduced some of the DSPy concepts, let's dive into the Google Colab notebook so I can show you some examples of programs, and hopefully that will help solidify those concepts in your mind. All right, so let's begin walking through the notebook itself. So as I said, this notebook will be linked in the technical article and it will be available for you to explore in your own time. The first thing to note here is that the notebook, if you are going to use any of the OpenAI models, you will need to have an OpenAI API key. How I like to read my API keys in is through a .yaml file, and I save this file in a location. Since this is a Google Colab notebook, you'll have to save it on a Google Drive if you'd like to access that. So I would find a location on your Google Drive from which to save a .yaml file, and you should save this down as OpenAI as the key, and the variable should be your API key, and that will be read in. It's also important to note that you should name the file API keys.yaml. I'll link to an example of the API keys.yaml file so you'll know how that file should be structured. The other thing here to be aware of is the output directory. So obviously I've saved the analysis down to an output directory, but you won't have this output directory. You won't have permission to save down here. So what you should do is change this to your own Google Drive directory, or just comment it out completely so that you are not saving the files down to an output directory. When I release this code to the public, what I might do is comment out any steps that save down to output directories so that you don't run into issues. Okay. So the first thing to introduce here is how we are building these programs, or for what purpose we're building these programs. So what we're looking at here is the GSM8K dataset. So the programs that I've built in this notebook are to solve math word problems, or word math problems, math word problems, worded math problems. So that's what we're trying to solve with these programs. So the GSM8K, I think it's the Grade School Math 8000. I think that's what it stands for. But it's a benchmark data set that has a bunch of worded math problems along with their answers. The reason I've chosen this task is because large language models by themselves have been notoriously bad at math. So there have been a lot of challenges with prompt engineering to try and improve the performance of base large language models to solve math problems. So I thought it was a suitable task to demonstrate a more robust prompt engineering approach, and maybe even apply some of the prompt engineering methods seen in research papers, but using the DSPy framework. So the GSM8K, it's available via Hugging Face, and you will be able to enter that link here. You'll see it's just leaving the Colab. That's fine. We will visit Hugging Face, and you can see here the types of problems that you have. So here's your math word problem, and then there's the answer. It's important to note here that the answers are given with the working out as well. So what I've done is just done a little bit of data manipulation to just remove the answer as a single response, rather than also getting this explanation alongside it. So that's all in the notebook. And the reasons for that is just to simplify things a little bit. You know, some of the models I have used are small, relatively speaking, for large language models. So it just makes it easier if you just have a single response as your label, instead of this kind of more verbose response here. Okay, so that's the data that we're operating off. So the task is, you know, trying to engineer a large language model to solve these types of math word problems that I've just shown on screen. Okay, so here's just various bits of data manipulation to get our GSM8K data in the right form. The next bit is setting up the models. So this notebook does work off two models. It works off the GPT 3.5 Turbo 16K API. So as I mentioned before, you'll need access to GPT 3.5 which is given for an API key. So you'll need to sign up to OpenAI if you have not already got an API key. The other model is the Mistral 7B Instruct version 0.1 GPTQ. So this is a quantized version of the Mistral model. And the reason for using this quantized version is because of the hardware resource allocated here. So I'm using a Google Notebook Colab Pro, which means that most of the time I can get access to a V100 GPU, which has about 16 gig of RAM, right? So I found that this Mistral model, the quantized version, can run on that hardware, and anything larger seems to crash it out. So that's why I've selected that model. And this is coming directly from Hugging Face. So it's important to note here, you can run the notebook with both. You just have to comment out the model, the GPT 3.5 model, and uncomment the Mistral model if that's what you want to use. And also make sure to comment this OpenAI wrapper, because you won't, if you're using the Mistral model, you won't be using the OpenAI wrapper, you'll be using the Hugging Face wrapper. So just uncomment this and comment out that, right? So just pay close attention here, and you should be able to run both models if you want. Running the notebook end-to-end does take some time. So it does take about half an hour. I haven't timed it precisely, but it does take time to run end-to-end. Okay, so before we get into the programs, just to make you aware, you can obviously change the size of your training data set and your evaluation data set, which we just call the dev data set here. So I've set mine to train on 5 samples from GSM 8K and to test on 20 samples, okay? So you can change this if you want. Obviously, the larger your train and test size, the longer it's going to take for the notebook to run end-to-end. So just be aware of that as well, okay? Oh, right. So let's look at some of the programs and how we define our programs. So programs are quite simple to define, right? We define programs as classes. So what I've got here is a single module program, meaning it's just made up of one module. This is the baseline. So I've deliberately created a baseline as a means of comparison to see what uplift I can get by creating more complex programs. So the baseline program just simply uses a predict module, which is already available from DSPy. And that's like a vanilla module that just makes a call to a large language model, doesn't do much else. So you define your modules in the init method within your program. So remember, your program is a class and you define the modules within the init method. So that's all you're doing here. You're just defining modules, okay? Now, within the module here, you set your signature. So there's 2 ways to set signatures. We'll come on to the second way of setting signatures in a moment. But what you see here is a shorthand method of setting your signature. So to set your signature in the shorthand method, all you need to do is type your input, which is a question, and deliver an output, which is answer, right? So that's your program, that's your module fully defined here in the init method. And then in the forward method, you define the logic of your program. So quite simply here, all we're doing is we're just calling that predict method. So all this program is doing is calling a predict method to make a vanilla call to a large language model of our choice. So notice here, I have not defined a large language model. All I've done is chosen a module, which is just a vanilla call to a large language model, and then defined the logic of that module. So all we're doing here is a basic predict. That's all we're doing here, just a basic predict operation. That's it. So this just makes a vanilla call to a large language model, and we'll get into what that looks like a bit later on when we inspect the prompt itself. So this is a program. This is a very basic program. And you can see the same thing here for a chain of thought program. The only difference here with a chain of thought program is that we use a chain of thought module. So the chain of thought module adds an additional step, a reasoning step before delivering an answer. And we still have the same signature. We deliver a question and answer. So that chain of thought module can operate on that question answer signature. And then the forward logic here is just self.predict again, which we defined up here. And that's just going to exercise that chain of thought module with that signature in mind for a given question. Okay. That's pretty much it. All right, so I'm going to just talk briefly about a more complex program. So this program is we'll move on to a slightly more complex program, right? So this program here is a multi-comparison program. So as you can see here, we have a slightly different way of creating more complex programs. So there's two aspects to this. There is the signature, which we have defined with a little more nuance. So instead of using that shorthand notation, we use a class, or we use classes to define those signatures. And you can see that we've also declared more than one module within the init method here. Okay, so let's start by looking at the program holistically, right? So the multi-comparison program. What do we mean when we say multi-comparison program? The best thing to do here would be to first show you on screen what this multi-comparison program looks like from a kind of schematic perspective, and then we'll talk about the code and how it relates to that. So hopefully what you should be able to see on screen now is the multi-comparison program schematic. I just find this is an easy way to show you what the program is doing first at a high level, and then we can talk and look at the Pythonic or the Python version of the program, and hopefully that will give you a better understanding of what's happening here. So the first thing we have is a question that's being asked, and it goes directly into a predict module. So instead of the predict module just delivering us one vanilla answer, so it is still a question answer predict. So you can see here, it's just asking us to predict. We're just asking the predict module to deliver an answer for a question. But here we have an arbitrary number of responses from the module. So essentially what we're doing is we're calling the large language model to give us an answer to the question an arbitrary number of times. As you know, large language models are stochastic in nature. So sometimes we do get variations in answers. And I think this comes out particularly when you're trying to solve logical problems, because large language models aren't particularly good at this just in plain prompting, just as standard. So what you've got here is a question gets sent as an input to the predict module, and then we ask it to deliver an arbitrary number of answers. So we can set n here, the number of requests, and it delivers an arbitrary number of answers. So you can see answer 1, answer 2, all the way to answer n. I think for the purposes of the notebook, I set n to 3. You can obviously set that to as many as you want. I think you will eventually run into limits with how many answers that you can feasibly run. But in theory, you should be able to set n to any number. The next stage is to concatenate all of the responses from the large language model. And that is fed in to the answer model as a context, right? So you give it the context of all of these answers to the question. So essentially, you're giving it n amount of candidate answers, and you're asking it to then look at those candidate answers, look at the question again, and almost reevaluate itself. So it's looking at those candidate answers, looking at the question, and then giving you a final answer based on those candidate answers and the initial question. So that's the multi-comparison module end-to-end. So that's multi-comparison program end-to-end. So that is a program that I just created based on two modules, two predict modules doing slightly different things. All right, so let's look at the Python code, and let's just see how this breaks down within the Python code itself. So having a look at the Python code, what you can see here is, first defining the signatures. So the reason I have defined the signatures with the class notations instead of the shorthand is because the signatures are a little more nuanced. We want them to do a little bit more. We want them to exercise a little more nuanced behavior than we can. What's the word I'm looking for? Then we can kind of direct just using the shorthand notation. So recall I said that your signatures should be precise and short. So this is my attempt at making signatures precise and short. So the first one is obviously to create the candidate answers. So what we do here is we have an input as an input field. That's the question. So that's just the initial question. It's important to know that it is the initial question. And at the top here, you need the description in here, but it's generate a candidate answer. That's what the signature is doing. That's the behavior of the signature. And then next we have the candidate, and that's the output. So the signature, we tell it that it's generating a candidate answer to the initial question. Okay. So the next signature is to select the best candidate response, right? So the best candidate answer. So you do need to be a bit careful with obviously how you're labeling these signatures. I think that should really say answer, but anyhow, it's worked as it should. So what you have here is the question. So that question is the initial question, and you'll see how that feeds in later. You have the context. So the context is the candidate answers, right? So these are all the candidate answers, all n of the candidate answers that you have asked the module to generate. And then the answer is described here as using the candidate answer to generate a response to the initial question. So it looks at the candidate answers and generates a response to the initial question based on those candidate answers. Okay, so how do we string these together in a program? Just like the single module program, we want to define our modules first at the top. And also you want to define your variables at the top as well in the init method. So the number of requests, that's a variable that we'd like to define. So that's defined here in the init method. Then we also have the generate candidate answer. So that's a predict module with the create candidate answers signature, which, remember, the signature defines the input output behavior of a module. Apologies. And then the number of requests. So this is how many requests we want to make to that module. Remember, we're generating candidate answers here. So we want to generate n requests to that module. The next module that we define is an answer module. So this simply just takes the signature. It's a predict module that takes the signature. But remember, this signature is a select candidate response. So this signature actually has 2 inputs and 1 output. So the first input is the question. The second input is the context. And the last input is the answer. So we have 2 inputs and 1 output. So remember that. That is key to understanding how this works. So the next step is to define the forward method. So this is the logic for which we are processing those modules or stringing them together for this program. Okay, so the first step obviously is we define an empty context list, because what we're going to do is we're going to loop through and concatenate all of the answers into that context. So then we create our candidate answer, right? So that candidate answer is going to do 3 completions of our large language of our module. So it's going to make 3 calls to that large language model for a given question. So it's the equivalent of you asking ChatGPT, let's say, the answer to a question 3 separate times. It's going to make 3 calls. So that's what we have here. We can then append those 3 calls into our context, and then create a context string. And then finally, we use the answer module, which we've defined at the top, to answer the question based on that context string. So hopefully that should be quite straightforward. As I said, take some time to explore the notebook. There is also some more complex methods, but I'm not going to go into the detail of those methods in this video. There is the technical article, which goes into more detail, and you can have a look at the notebook as well for your own benefit. Okay. The next step here is just defining our performance metrics. So because we're looking at math problems, the performance metric we're looking at is correct answers or exact match. So we want to score this model we want to score the program such that if the answer is correct, then we want to score it based on the correctness of the answer, right? So we're just using a basic score of correctness here. That's it. So that's all we're doing here. That's what this cell of the code is doing. It's creating our performance metric. That's it. Here's a little bit of information on the teleprompter itself. So the teleprompter, in short, uses a bootstrap teleprompter, which has a teacher method, which has a teacher model, and the model that we use within the program itself. So usually the way it works is you want to take a teacher model that's a bit more powerful than the model you're using within the program, and that creates bootstrap samples from your data to guide that models to almost like help that model generate appropriate prompts to answer those questions, to help that program generate appropriate prompts to answer that question. So that's roughly at the high level how it works. What I would implore you to do is have a look at the notebook and just read through this. It will explain it a lot better than I can over video. But essentially, remember, the teleprompter is there to compile our programs so that we can optimize the prompts generated from those programs. And that's going to become clearer as I step through and show you what those generated prompts look like. So here we're defining our teleprompters. It says define compiler, but actually, yes, we're defining our teleprompters. And then we run our experiments. So the way I've set this up is to run the baseline or to run a program where it's uncompiled, just as a baseline to see how that performs. And then I've also run the compiled version to see how that performs as well. So I've introduced the baseline program, which was the single module program, the chain of thought, and the multi-comparison as well. So we can take a look at these programs to show you what they look like before they've been compiled, how they perform before they've been compiled, and the same two things after they've been compiled. So let's just have a look at the baseline, right? So what's neat about DSPy is it does provide you with an evaluation, a built-in evaluation function. So you can use your data. So remember, we defined our data set, our development data set, as our test set, and we can test our program out on that. And that's what this is doing here. So we're just testing that program, the baseline program, against our test data set. So here are the results, and I've formalized these down below, but we got a score of 45%, so 9 correct answers out of 20. So that's baseline without really any prompt engineering, just asking the module, asking the program, setting up the program so that it just asks a model a question, returns an answer. We get a score of 45%. So that's what that looks like. And just to show you, so we are going to jump around the notebook a bit here, but you can explore this in your own time. But just to show you what that looks like when we ask the program to generate that response. So remember, this is uncompiled. This is what that looks like. So if we step down, that's chain of thought. Here's the baseline, right? Okay, so let's if we ask the baseline a question, so that's the baseline module, that program that we defined. We can ask the baseline a question. That's the question we ask. So the correct answer to this question is actually 60%. So that's the question. You can see it delivering the answer. And then what's neat about this is we can inspect the prompt itself. So the thing to note here is the green text is what is generated, right? And the white text is the prompt itself. So you can see the prompt, right? So this is all created from that baseline program, the class that we defined earlier. So we didn't write a word of this. Really, this is created from this, created from that class, right? So it's very basic. It says follow the following format, question, and then your answer. So there you go. And then you have your question, which is delivered, which has been delivered into the program itself. And then the model, the program responds with an answer. And there's your answer. So there you go. Therefore, he has covered 7.5% of the total distance. So just take some time to explore that yourself and get comfortable with this output. Okay. So let's step back up and let's explore the compiled version of the baseline. So for the compiled version of the baseline, we actually get an uplift in performance. So this is the same baseline program. It's just a vanilla input output, but we get an uplift. Oh, no, sorry, apologies. For the compiled version of the baseline, we don't actually get an uplift. It's the same level of performance, right? So we still get 45%. Apologies for that. That's I skipped ahead there. But yeah, we have 45% performance. But just to show you what the prompt generated from that program looks like, I'll scroll down. So if we go down there, so this is the baseline. That's baseline forward. And here we go. Here's the compiled baseline, right? So this is what the compiled baseline does, and we ask it to produce an answer to the same question. And if we inspect the history, what we can see here is, again, remember the green is what has been generated by the program, but the white is the prompt. So this is effectively like your prompt template, and that's been generated also we've compiled that, right? So that's been generated for our compiler, using a teacher. So what it's done is it's taken our training samples and bootstrapped them into the prompt. And that's using the teacher method, using the teacher model to do that. So in this case, I've set the teacher model to be the same as the model used in the program. But ideally, I think you want to set it as a more powerful model. So you can see here, it's taken out some samples and attached them to the prompt here. So anytime we ask a question, it will come with that prompt, and then the answer will be generated here in green, right? So we've got an answer of 37.5%, which isn't quite correct either. And you can see the format of the answer isn't quite correct either, because, you know, we've got this question, Michael, blah, blah, blah. But actually what we want is just the answer, right? So that's all to do with the way the program is set up and the way the model, or the way the teleprompter has worked to compile that program. So saying that, let's have a look at the chain of thought program to see how that has compiled. So let's move on to the chain of thought program, right? So the uncompiled version of the chain of thought program actually gives us a slight uplift on even the compiled version of the baseline. So completely uncompiled, our chain of thought program produces a 55% score. So 11 correct answers out of 20. And the compiled version gives us an even greater uplift of 13 correct answers out of 20. So then we can go down and have a look at what that looks like. What type of prompts are generated there, right? So that's the baseline. Let's have a look. So here's chain of thought. Again, so if we inspect the history for chain of thought, let's just make sure that's correct. So that's a chain of thought. So you can see here that the uncompiled version pretty much delivers gibberish. It almost looks like it doesn't know what it's doing, which is fine. It's kind of expected. We've got a more complex program, so it needs compiling. But then if we look at the compiled version, what we see is it actually generates the correct answer, right? So what it's done is now it understands it needs to deliver a question, reasoning, and answer. So that's based on the program that we specified, the chain of thought program. So it's then bootstrapped some examples from our training data set. So that's where, this is flexible, because this program has been compiled specifically for our training data set. So, we know that it can operate within the domain that we want to use the program in. So you can see it's bootstrapped example. So instead of just question answer, we've got question reasoning answer. And then last, what we have is the actual generated result. So the question we asked is this same question about Michael traveling interstate. And then we've got a reasoning step. So then what's generated by our program is this. So this is off the back of that prompt template. And that answer is the correct answer. And you can see the form here is a lot neater and easier to follow. We can see the question, reasoning step, and answer. But just in case this is a little confusing to you, the teacher model is used to generate this prompt for us. So that's a bootstrap prompt. So this is compiled using the teacher model based on our program definition. And then with that prompt template, so we haven't written a word of this. This is just compiled based on our program, the model we're using, and our data. And then the prompt, we use that prompt template to ask the questions, and we can get a response. And what we've seen is that, this type of program does actually improve the performance of the baseline model, which is fantastic. Okay, last, let's just have a look at the multi-comparison program that we defined. So first of all, we'll look at the results of that program. So here's the multi-comparison. And at the top here, we're starting off with 55% uncompiled. So 11 out of 20, it gets right. And then when we do compile it, we do actually see a loss in performance. And sometimes this can happen. Like I said, it completely depends on how you compile it, how long you compile it, the complexity of your program. If you use a more complex model, so we also had some timeout errors here as well, which can cause some issues. If you use a more complex model, so if you use a more sophisticated model as your teacher, you can get an increase in performance. And I have compiled this to get an increase in performance before. But I'll show you what that compilation process looks like anyway. That's chain of thought, that's analogical reasoning, and that is, here we go. Here's the multi-comp, right? So with the with our multiple comparison program, you can see here that we have asked the model to generate 3 candidate answers, right? So off the back straight away, this uncompiled, so there's no bootstrap samples here. We've just got 3 candidate answers generated raw, and then there's the answer. There's the output from the program, okay? So that's our multi-comparison program, uncompiled. So let's see what the compiled version looks like. And no surprise, what we have here is what looks like quite a messy prompt, but actually what we're doing is we've bootstrapped some responses from our training data, right? So we want to generate 3 candidate answers. So this is an example from our training data. We've generated 3 candidate answers, and then we've responded with an answer here as well. And it's done that for a few examples from our training data, to the point where that becomes our guiding prompt. So if we ask the model a question, we'll have this prompt as a context. And you can see the context outlined here. So there is your context. And if you explore this, you'll see all of these things exist in the context. And then here, we're doing exactly the same thing. So Michael is traveling on the interstate. We generate our context. We've got our 3 candidate answers. In this case, it's saying the same answer every time. Again, you can play around with things like the temperature setting to make sure it's delivering a diverse set of answers. And then there you go. So Michael has covered 450 kilometers, which is 7.5% of the total distance, which is incorrect in this response. But just to illustrate how these programs do generate the prompts for us instead of us having to write these prompts out. Okay. So hopefully the notebook has given you a better understanding of the DSPy framework and how that works, and also how instead of hand typing our prompt templates, we simply write a program, and that program is compiled to generate those prompt templates for us. And hopefully you've also seen how, if you can compile your programs in the right way, it can improve the performance of your model on certain tasks. So the takeaways are that, when we're compiling, when we're doing prompt engineering with DSPy framework, we aren't writing out prompts by text manually. We're writing programs, and we're compiling those programs based on data and based on a particular model. We can use different approaches to compile the program. So I use the bootstrapped few shot teleprompter available out of the box from DSPy, but there are other teleprompters available as well. So it's worth experimenting with the different ones to see which ones are most performant for your task. I didn't cover all of the programs. So there is another program in the notebook. It's an analogical reasoning program where you essentially write a program to do to create some analogies before it responds to the question. So check that out when you have a chance to review the notebook for yourself. Thank you, and I hope that you enjoyed this video. I hope you found what we discussed today informative. I really think the framework does hold some promise for the future, and I'll be investing more time into building more applications based on the DSPy framework. If you found this video informative, please do like and subscribe to the channel for more insights on artificial intelligence, data science, and large language models. Please feel free to comment if you've used the framework before. And I look forward to seeing you in the next video.